Okay, let's look at a couple problems to help you review for your final exam. So we first started off talking about limits. So most limits we talked about were direct substitution. But if they weren't, there's always a way to get around that. For example, this first one is a trigonometric limit. It has sine of 7x cubed over 14x cubed, which if you plug in 0, you're going to get the sine of 0 over 0, which is undefined, undeterminate. So somehow we have to figure out a way to rewrite that with our special trig limit, the limit of x as x goes to 0 of sine x over x being 1. Now in this case, we don't necessarily have that. We have sine 7x cubed on the top. So if we want this limit to go to 1, then we need 7x cubed on the bottom. Which is fine, you can write that, but that's not what we have in our problem. We have 14x cubed. Well, we know that 2 times 7x cubed will give us the 14x cubed. So this is simply just 1/2 times the limit as x approaches 0 of sine of 7x cubed over 7x cubed. So that's just 1/2 times 1, which is just 1/2. So sine of anything over that same quantity will always tend to 1 as x tends to 0. Now, just like the first problem when I plugged in our value, the value that's approaching, which is the first thing we should always try, on number 2, I'm also going to get a 0 over 0 limit. So if I plug in for number 1, or plug in 1, I'm going to get 1 squared minus 3 times 1 plus 2 over 1 minus 1. So that's going to give me 0 over 0. So the three main ways we got rid of 0 over 0 limits is we did the trig trick with the sine over x, or some of the cosine ones, or we factored, or we used the conjugate. So since this one doesn't have a square root, not really a conjugate problem, so I would just go ahead and factor. So if I look at the top, two things that multiply to positive 2, add to negative 3 are negative 2 and 1. And then t minus 1 still on the bottom. Now the benefit of doing this, obviously, is if you look, we have this common factor that cancels out. We're left with the limit as t tends to 1 of simply just t minus 2. No denominator anymore. So now this is going to be an easy direct substitution. 1 minus 2 is negative 1. Alright, so this one we have a limit as x tends to infinity. Now the trick to doing limits at infinity is we want to always look at just the term that has the highest power. One way we did this earlier in the year is we would divide everything by the highest power to every term. Same idea. So this is simply going to be the limit as x approaches infinity of x to the 6 over 2x to the 7th. So now we can just determine what these leading terms have, and what happens to those is they tend off to very, very large numbers, and we'll get our solution. Now x to the 6 over x to the 7th is simply going to simplify to 1 over 2 to the x. So plugging in infinity for x, putting in a very, very, very large number, we're going to have, 1 over basically the largest number you could ever imagine. So if you have 1 over the biggest number you could ever imagine, then that is going to tend to 0 as a limit. Remember the definitions. A number over infinity will tend to 0. Infinity over a number will tend to infinity. So kind of the reverse idea is there. Now 4 on its surface looks kind of like a mess, but I can tell right away it's going to be a 0 over 0 limit. Because if you notice 0 here on the top, definitely going to be 0 on the bottom. Cosine of 0 is actually 1, so it's not 0 over 0, it's 1 over 0, but 0 on the bottom is still bad. Now, ironically, we can actually deal with this one similar to we did number 1, just doesn't appear that way. So if you notice that we have cosecant on the denominator here, which I can't do a whole lot with. Cosecant of 0 is actually 0 as well. But if you remember, 1 over cosecant is also sine. So I can actually rewrite this limit, not really doing a special trig, just doing trig identities. I could write this as cosine x, and then this cosecant could come up on the top as sine x over 4x. Now this is still 0 over 0, but if you notice, we have sine x over x, and we know sine x over x goes to 1. So you could think of this as the limit as x goes to 0 of cosine x over 4 times the limit as x goes to 0 of sine x over x. Now if you plug in 0 for cosine, you get 1. So this is simply 1/4 times 1, which is 1/4. Let's look at number 5. Now 5 is pretty obviously the other kind of big 0 over 0 limit we have. Because if I plug in 0, definitely 0 on bottom, and on top I get radical 3 minus radical 3, so this would be a 0 over 0. So besides factoring in our trigonometric stuff, the big idea here is we can multiply by the conjugate of the numerator. So if you recall how we did this, we would multiply top and bottom by radical 3 minus t, opposite sign, so it'd be plus in this case, radical 3 minus t plus root 3. Now hopefully when we clean this up, a lot of good things is going to happen. So we have limit as t tends to 0. On the bottom I get t, radical 3 minus t plus radical 3. And remember, you don't want to distribute that because hopefully that t will cancel. On the top, when I FOIL, I get 3 minus t, and I get minus 3. Now, you could do the inner and outer term, but it's going to be basically the same thing, opposite terms. So if I cancel those 3's on the top, I get negative t over t, radical 3 minus t plus radical 3. Now this is still technically undefined, but now I can get rid of those t's, and it's going to be negative 1, and then I can plug in 0 on the bottom. So 3 minus 0 is going to be radical 3 plus another radical 3, negative 1 over 2 radical 3. All right, let's look at number 6. 6 says, what is the limit of 2 secant x as x approaches pi from the right? Now, on its surface, this looks like maybe a difficult problem, but remember, the first thing we should always do is plug in pi. So, what is 2 secant pi? Now, if this is not undefined or dividing by 0, it's not an issue. Secant is the reciprocal of cosine, so I could also write this as 2 over cosine pi, which is 2 over 1, which is just simply 2. So no real issues there. It's really just a plug-in limit. Now, the plus, remember, means what happens as it approaches from the right, and the minus would be what happens as it approaches from the left. Alright, so the final one on this first page says, for what values is f of x a continuous function? Explain your answer. Okay? So a couple things. For something to be continuous, remember, we need f of a to exist. So right away I can eliminate a lot of things, right? So right away I know x can't be 0. I know x can't be 2 or negative 2. And those are just things that make the bottom 0, right? Can't be 0, can't be 2, can't be negative 2. Cosine always exists, that's fine. The square root, though, square roots have to be positive. So I know that x has to be bigger than or equal to 0. So just from the first condition that the function must exist, I essentially know that I'm having x's that are greater than 0, because it can't be 0, remember, but also can't be 2. So we really don't care about the -2 part because it has to be bigger than 0 because of another part of the function. So it has to be bigger than 0 except 2, for sure. We know the limit has to exist as x approaches a. And this limit does exist as long as the bottom is not 0, and we've already eliminated that over here, so that's fine. And then it has to be a plug-in limit, and this certainly is a plug-in limit when it's not, when they're not at those undefined values. So remember, this has to just equal the plug-in limit, which it does. So basically, this function is continuous. We would say bigger than 0, but not including, all the way up to 2, skipping 2 and going to infinity. So you're just looking for places where this has all three of these conditions met. And the big one is obviously going to be where it's undefined. Undefined is going to be the one that usually gives us our issues. Okay, let's look at some of these derivatives. So if you notice, he says find the following derivatives with respect to x. You do not have to simplify. Now, we've been recently working on antiderivatives, so now we have to work on derivatives. So go back to our power rule and our quotient rule and our product rule and our chain rule. So that can be a difficult thing to go back and forth between. So this one says y equals x over natural log of x. So we have two things divided, so this is going to be a quotient rule. F prime g minus g prime f over g squared. So the derivative of x is simply 1 times the natural log of x minus the derivative of the g of x, which is the natural log, it's 1 over x times f, over natural log of x squared. I'm going to write it like that. Now the only thing that you can really see here is you don't have to simplify at all. This would be fine, and this is how they typically word it on the test. I'm going to cross that x out just because it's going to bother me if I don't. So ln x minus 1 over ln x squared, which is pretty much the best this can turn into. All right, so if you look at 9, so 9 has the form of a chain rule because it has something inside a function. So if I consider the inside u equals 1 over x squared, or I could think of it as x minus 2, then remember the derivative of the inside, u prime, would be negative 2x to the minus 3. So our outside function, this is our inside function. Our outside function is simply just cotangent of u. So if you recall the derivative of cotangent, cotangent is negative cosecant squared of u. But our u, remember, our u is going to be 1 over x squared. But then in the chain rule, you have to take you have to multiply it by the derivative of the inside. So that's going to be times negative 2 over x cubed. So just to make it look prettier, I could write it as 2 over x cubed, because the negative and the negative, cosecant squared 1 over x squared. Again, I should mention on this one, you really didn't have to simplify. You could have kept it like this, but, you know, it doesn't hurt to simplify a little bit. All right, so 10, again, not really a quotient, not really a product. So again, one of those chain rule kind of problems. So the inside in this case is going to be x cubed plus sine x plus 3, which in itself, sine does have an inside, but it's just x plus 3, which has a derivative of 1, so not a big deal. So u prime is 3x squared. The derivative of sine is cosine, so cosine x plus 3. And then our outside function is simply going to be h of x equal e to the u. Now we know the derivative of e to the u is just simply e to the u. So you could write it as e to the u, that's fine, times the derivative of the outside, which is, or inside, which is 3x squared plus cosine x plus 3. But then just remember, we got to make sure we put the u back in, so our final derivative is going to be e to the x cubed plus sine x plus 3. And you do have to plug that back in. That would be something that you'd have to make sure you do. Times 3x squared plus cosine x plus 3. Next one is pretty obviously a quotient rule again, because it's, you know, two things divided, f and g. So again, f prime g minus g prime f over g squared. Now I'm kind of nervous about the bottom, because when I start to do the derivative here, the derivative at the top, nothing big, nothing too terrible. 12x squared minus 1 times g, that's fine, that doesn't change, tan of sine x. Minus, now the derivative of the bottom here is kind of tricky because the bottom has an inside of u equals sine, which has a derivative of cosine. And then the outside function is, of course, going to be just tan of u. Now the derivative of tan is secant squared of u, but u again is sine. But then we're multiplying it by this factor of cosine. So that's all just the derivative of g squared. And then it gets worse because now we have to multiply it by f, which is 4x cubed minus x plus 1, as I'm out of room. All over g squared. This is one I'm definitely not going to simplify. Tan of sine x squared.